This is our second question in finding the arc length. And when you saw the first question, you might have questioned, why are we doing such a strange function? This was my question. Seems like out of nowhere. You probably have never seen a graph of something like this. And the truth is that even though we've managed to find the formula a to b integral of 1 plus dy over dx squared dx as something we can use to find the arc length, this integral in most cases will be something you can't calculate. You can't calculate. We already know that not all integration can be done, right? That's why we have like approximation methods, like Riemann sums. So just to give you an idea why that is so, I just put something that's really easy. Like not easy in terms of the actual problem, but so actually it's not easy. I'm trying to say this is a problem that seems so simple that we feel like we should know the answer to. Okay? But it actually turns out that it's not that simple. Now let's just draw this graph and see why. We all know the graph of y equals x squared, right? And we're just drawing from 0 to 1, so it's this part of the parabola. This is 0, 0. This other point is 1, 1. What's the length of this straight line? What's this length? Ah, this length.
1.
It's 1 and 1, so what's this length?
1.
No, 2.
No.
Squared plus
square
one.
root of 2.
So 0.5. No, it's just 1.
No.
No, square root
It's
of
2.
2, it's just the root.
Here's 1, right?
Yeah.
So this side will be square root of 1 squared plus 1 squared.
So square root of 2.
This will be square root of 2. What is the value of square root of 2?
Square root of 2.
It's approximately 1.414. Okay? You should know values like this.
Do you need to remember that?
Yeah, you should try to memorize that, okay? Because it does come up. You want to memorize the approximate values of square root of 2, square root of 3, square root of 5, square root of 6. Yes?
So is there a way to actually calculate square roots, or do you just have to memorize them?
There is a way to calculate it, but it takes so long that it's better to just memorize these. Okay. All right. Okay, so going back, we know that this dotted line has length 1.4, and therefore this length should be what? Bigger than 1.4 or less than 1.4?
Big.
Bigger than 1.4. Should be, it's longer, right? Yeah. So we know that it should be bigger than 1.4, but we don't know how larger. But this seems like a natural question to ask. Like you get a piece of parabola, and the question is, what's this length? Shouldn't we be able to answer that? Right? Amazingly, if you actually try it, it's really hard. So if I try to do the solution, the formula would be square root of 1 plus dy over dx squared dx. Goes from 0 to 1. And dy over dx is 2x. Right, that's the derivative of this one. So it's 2x, so it's going to be 1 plus 4x squared. And now you get stuck. Would you know how to do the integral? You can't. I mean, you can try. Don't write this. Let's say you have, say, something like this one. And say you square both sides so that you get u squared equals to 1 plus 4x squared, and then differentiate both sides, 2u du equals to 8x dx divided by 8x. And then you can rewrite this as like, this is our u, dx is 2u over 8x dx. You get something, but because you still have an x that's not canceled out, yes?
Wouldn't dy dx equal to 2x, not 4x?
You squared it.
Right, and then wouldn't that be 2x squared?
What? 2x squared is what?
It's 4x.
Okay. So if you try to do this integral, you realize that you still have an x, which means you have to solve this for x. And that gives you u squared minus 1 divided by 4 equals to x squared. Take the square root. That goes here, and then you get something that's even worse.
It's more complicated.
Yeah.
Try the widen.
Huh?
Did you try the widen?
Did I try what?
Can you try like dy?
Oh, okay. So last time we had two formulas, right? One with this one, or the other one was dx dy, and that doesn't help either. Yeah. It's not any better. Okay. So there is actually a way to do it, except that method is something that we haven't covered. You need to use something called hyperbolic trigonometric functions, or hyperbolic functions. So you set x as 1/2 sine hyperbolic of u, then you can do this integral. But even with that, the answer is really crazy. Now, that's why we had such a weird example in the first one. Like the ones that you can do, there aren't many. You have basically like 4 different types that you can do. And I'll just be covering two of those today. So this is almost like impossible to do. Okay? You could do it with some harder math, but it's almost impossible. So that's why I didn't say ask, say find. It's approximate. How do you approximate an integral? Well, one way is to use your calculator, right? But how does your calculator approximate the integral? Does it find the antiderivative? No.
Just plug values in?
Yeah, and
Minus the first and the initial.
you use the Riemann sum. Right, yeah. And of course, the best one is the Simpsons Rule. So your calculator will be using Simpsons Rule to find this value. For us, it becomes so hard. So let's just use 2 intervals. Okay, so from 0 to 1, I'll just choose 2 intervals. So delta x would be b minus a divided by 2. And then x0 is always the left endpoint. What's x1?
1/2.
1/2. You just move by this number, right? Delta x, right? What's x2? 1. Because you keep adding 1/2. 1/2 plus 1/2 is 1. And you're at the right side already. If you have just this much, I guess one way to do it would be Simpsons, but that's like too simple. Let's try trapezoidal, okay? Trapezoidal approximation. Do you remember the trapezoidal approximation? What's the formula?
Delta x over, I want to say 3.
2. The 3 one is the Simpsons.
And then it's
The first one is f of x0.
and then plus 2.
2.
F of
f of x1, and then you go,
The
the last one is nothing, but already here at the last one, x2 is the, so this is x0, that's x, you have x0, x1, and then x2, so that's fx2. And delta x, we found it to be 1/2 divided by 2. F is not that one, but this one, because we're trying to find the approximate value of this. Okay, so this is our f. What's f evaluated at 0?
1.
1. If you plug in 0, you get 0, square root of 1.
Oh,
You get 1. Okay, twice. What's f evaluated at 1/2? Well, 1/2 squared is 1/4 times 4 is 1. 1 plus 1 is 2. So square root of 2. If you plug in 1, you get
4
plus 1, 5, square root of 5. And approximately, this is like 1.4. This is about like 2.2 something. So you get 1/4 of 1 plus 2.8 plus 2.2, and it's about 1.5. We can actually figure out that this is a slight overestimation if you draw the picture. Yeah, I wouldn't go that far. So the actual answer is slightly less than 1.5. It's like 1.47 something. But if you wanted, we can get a better approximation by not having 2 intervals, but like 4 intervals or 6 intervals. The higher we go, better approximation we have. And also we can use the Simpsons to get even better approximation, the same number of intervals.